Okay, yeah, thank you very much to the organisers for allowing me to talk at this nice conference. Yeah, as they alluded to, my name is Michael Kenna-Allison, and I'm a PhD student at the ICG, which is the Institute of Cosmology and Gravitation in Portsmouth. And I'm going to talk to you today about work that me and my supervisors, Emir Gumrashoglu and Kazuya Koyama, have done on the stability of a model of massive gravity called generalized massive gravity. So the outline for my talk is follows. I'm going to first of all start off motivating slightly why one may want to consider and study modified and massive gravity theories. Then second, I'm going to go and sort of outline a few problems with massive gravity cosmologies and the difficulties in trying to get a stable dark energy solution. Third, I'm going to introduce generalized massive gravity, which will be abbreviated to GMG, which could maybe outline, sort of give a path away from the instabilities and maybe give us a stable solution. And then in the fourth section, I'm going to give you a concrete example and outline and show you that you can indeed have a stable dark energy model from generalized massive gravity. And five, I will summarize. So the motivations. So a lot of you will have seen these motivations before. So first of all, why study modified gravity? A lot of interest in modified gravity theories came about with trying to solve the cosmological constant problem, or to kind of get a late time acceleration of the universe by modifying gravity and cosmological scales without introducing a cosmological constant. But secondly, which is also, I think, is a very important and very interesting thing to do, is to modify GR, so like beat it up in as many ways as possible, add extra degrees of freedom, modify it in different regimes, and test all of these different theories, and to see whether or not these behave better than general relativity. So it's important to understand the nature of gravity on universal scales by sort of beating GR up, if you will. So then these are sort of a couple of the motivations for modified gravity, but why massive gravity? And so massive gravity is actually what's known as technically natural extension of general relativity. And by this, I mean, if you take GR and you deform it by a small parameter, in which this case is the graviton mass, and then you send this parameter to zero, you get a symmetry which is restored, which is the diffeomorphism symmetry of GR. So this is what I mean by technically natural. And what is also a nice feature of massive gravity theories for cosmology is that the graviton mass gives a long-range modification of GR. And these sort of massive gravity theories have been shown to have self-accelerating properties. So therefore, these could be a candidate for dark energy. But also, why one would maybe want to study massive gravity is that there exists a nonlinear theory of massive gravity called dRGT, which stands for the authors, so Claudia Durand, Gregory Gabardadze and Andrew Tolley. And this is a very non-trivial thing. So it's very difficult to write down a nonlinear theory of massive gravity. And this was finally done in 2010. There's a lot of nice reviews in the literature sort of detailing the journey through the history of, first of all, when Fields and Pauli proposed a massive spin-2 theory of gravity, which is a linear theory, all the way through to 2010, where we were able to write down a consistent nonlinear theory of massive gravity. So what does the theory look like? The Lagrangian consists of a kinetic term, which is Einstein-Hilbert, which we don't modify. And then simply the modification from the graviton mass comes in the form of a potential, which is built out of the interaction of two metrics, G and F. G being the dynamical metric and F being a background fiducial metric. And then you can have whatever matter Lagrangian you want. So taking a closer look at the potential, it's built out of these polynomials Ui, and these UIs are built out of, like as I said, an interaction between a dynamical metric G and a background metric F. Now, this background metric F is fixed by Force-Zuckerberg fields, and these are introduced to restore diffeomorphism invariance. So if you take anything from this slide, all this dRGT Lagrangian is a potential which is built out of the interaction of two metrics. And so you can say, what I think is a useful thing to do is do a degree of freedom count to show that we actually can get 5 degrees of freedom expected from a massive spin-2 field. So to start off, we have 10 degrees of freedom in the G metric, and then we have an extra 4 from the Force-Zuckerberg fields here, which is 14. We're able to remove 8, 4 by gauge freedom and 4 by non-dynamical degrees of freedom, which leaves us, with my math is correct, with 6. And then so therefore we need to remove 1 degree of freedom. And the whole point of dRGT, of this potential, is that this potential allows us to remove 1 more degree of freedom, called the Boole-Weddeser ghost. And then this gives us the expected 5 degrees of freedom from a massive spin-2. So now we have a fully consistent, ghost-free, nonlinear theory of massive gravity. And now we can take it and start to apply it to cosmology. So now I'm going to tell you about the problems with massive gravity cosmology. So as I said, it's a nice review here by Claudia, sort of detailing the cosmological applicability of massive gravity theories. I'm not going to go into too much detail, but try and outline a little bit of the problems. So as a general rule, in massive gravity cosmology, you have two solution branches. One is self-accelerating and one called the normal branch. Self-accelerating branch sounds like a nice way to go, but unfortunately, there's a nonlinear ghost instability down here. So this forces us to choose the normal branch, which then forces us to choose a form for our fiducial metric. We can have flat, which prohibits expansion. We can have a maximally symmetric spacetime, which is de Sitter or anti-de Sitter. And if we choose de Sitter, we obtain a Higuchi ghost. If we choose anti-de Sitter, then we have no acceleration. So this sort of looks pretty bad in terms of massive gravity cosmology. But as you'll see later, there are ways of getting around this and sort of adding extra degrees of freedom or field dependence to maybe getting a stable dark energy model. So now I'm going to go into a little bit more detail, one of the problems with the self-accelerating branch, which is the strong coupling problem in dRGT. So down the self-accelerating branch, there's a strong coupling issue in the vector and scalar sectors. And I'm going to briefly show you how this comes about for the vector sector. So schematically, consider the action for the vector modes. It's essentially a kinetic term minus a potential term. So in dRGT, massive gravity, what we want to do is look at the coefficient of the kinetic term. And we find that the coefficient of the kinetic term is proportional to this polynomial function j. And this is a function of xi. And all xi is the ratio of the scale factors of the two metrics. So then we use our background equations on the quadratic action. One of the background equations tells us that j is equal to 0. And if j is equal to 0, this shows that the kinetic term is vanishing because t, the kinetic term coefficient, is proportional to j. And therefore, this indicates the strong coupling problem. So this is pretty bad. So what we do, what theorists do, people who do massive gravity cosmology do, is try and look to extensions to dRGT to find stable cosmologies. One such extension you could imagine is bigravity, which is where you promote the background reference metric f to a dynamical variable. This gives us 7 degrees of freedom. So already we're introducing new degrees of freedom. You could think of a quasi-dilaton massive gravity where you introduce an extra scalar field. This is also shown to be unstable. So these two are unstable models of dark energy. I should stress. And there are many other models which you can have, all which break various assumptions. So minimal theory breaks Lorentz. Mass varying massive gravity introduces an extra scalar field. But what I want to tell you and to try and sell to you is that generalized massive gravity introduces no extra degrees of freedom. And what we want to do is that this theory has been largely unexplored perturbatively, and this is sort of the subject of this work. So we want to take generalized massive gravity with the fact that it's not introducing any degrees of freedom and look at the perturbative stability. So what is generalized massive gravity? So here I'll show you the action. So you'll notice it's very similar to the action of dRGT, except these constant parameters, the alpha i's, are promoted to functions of the phi A, which are the Stuckelberg fields. So like I said here, so this action preserves global Lorentz symmetry, but breaks translation invariance. So if we shift phi A by some CA, this can be seen to be breaking translation invariance because the mass term becomes dependent on this combination. And so the stability of this theory has been shown of exact FLRW solutions in the decoupling limit, but sort of the perturbative analysis hasn't been explored yet. And so this is the subject of this talk. And my claim to you is the following, is that GMG does not exhibit the same problem of vanishing kinetic terms as dRGT. And this indicates the lack of a strong coupling problem. And so now we're going to prove this to you. So first of all, again, we recall our action for our theory. And for the matter sector, we just consider a k-essence fluid, where x is the kinetic term for some matter field, for some matter scalar field. And the reason why we do this is because it has the advantage of being able to have a fluid description. So step one, what we want to do is we want to calculate the background equations. I'm not showing you them all, I'm just showing you the relevant ones. So the top one here is the Friedmann equation, where m squared L is the effective cosmological constant arising from the mass term, where L is again just a polynomial. And what the important equation though here is the Stuckelberg equation, which in dRGT tells us that J is 0. In generalized massive gravity, we get a contribution. So we find J is proportional to the time derivative of L, and we find that this is non-zero, and this will become important. So step two, we want to calculate again the quadratic action for the vectors, and we find that it takes this form. So again, we have like a kinetic term minus some gradient or potential term. And step 3, we want to check the coefficient of the kinetic term, so this tau. And again, we find that tau is proportional to the same polynomial j, but this time we find that it's proportional to the time derivative of this L, and it's non-zero. And so this is non-vanishing, and this indicates a lack of strong coupling. And so you can say that this theory doesn't have the same problem as dRGT in terms of strong coupling. But you can't just say that this theory is stable. What we want to do is we want to check the absence of gradient instability and ghost instabilities. So here I'm doing it for the vectors. So to check the absence of ghosts, we want to again take the coefficient of the kinetic term, and we want to do a UV expansion.
There is a question by Chun-san.
Chun-chan.
Please, could you please go back to your last slides?
Yes.
This alpha is a function of phi A, right?
Phi A, indeed, yes.
And phi A is Stuberg scalar field, right?
Sorry?
Phi A's are Stuberg scalar fields.
Stuckelberg scalar fields, yeah. So
Yeah.
phi A, so I should note that phi A goes to so we choose the unitary gauge for the F metric, and phi A goes to minus f of t squared, which is like, so it's basically alpha I is a function of time.
Oh, now I'm confused because phi A, there are 4 Stuberg scalar fields, and they take the VF align with the coordinate of space and time. And why this phi A is only, give you the function of time instead of a function of space and time?
So why does it only give function of?
Yeah, because of phi A, there are 4 scalar fields, and then phi A, one of them equals to time, and the rest of 3 of them equals to x, y, z, these 3 special coordinates, and then it breaks the homogeneity of space and time. Maybe I missed something.
So we want to ensure that they respect the same symmetry as the G metric. So we actually, to ensure that this, let me think, that this ensures the same, so homogeneous and isotropic, there is a form of phi A, and there is a form that which you choose to Stuckelberg fields. And so so it's actually in the paper we have the form which this should take. And if you want, we can talk about it later. But it's a little bit complicated, and I don't think I have enough time to explain now.
So your point is by choosing some internal metric, but at the end, phi A is homogeneous.
It is homogeneous, yes.
Okay. Let's get to detail later.
Yeah. Okay. So, yeah, what we want to do is check for the absence of ghosts and gradient instability. So the absence of ghosts, we want to check the coefficient of the kinetic term in the subhorizon limit, which is equivalent to sending k to infinity. And we obtain a relation like this. And so to check the absence of the gradient instability, we want to check that the sound speed squareds are positive definite in the UV limit. And we obtain this relation, where gamma can be corresponding to like the mass of the tensors. So then we want to look at the scalars. So at the beginning with the scalars, we have a setup with 5 degrees of freedom. When we integrate out non-dynamical degrees of freedom, we can reduce to a system with 2 degrees of freedom. So the system is formally now this, where K, G, and M are 2 by 2 kinetic, mixing, and mass matrices, and psi is our field array of the 2 scalar fields. So the question you can ask is the system stable? And so we check the no-ghost conditions and the squared sound speeds and the positivity of the squared sound speeds. So to get the no-ghost conditions, we check the eigenvalues of the kinetic matrix, which are given by these. We expand the eigenvalues in the subhorizon limit to obtain an expression like this. To avoid ghosts, we require that both of these are positive. And you can see you can identify E1 as the null energy condition for the K-essence fluid, and E2 as can be identified as the scalar graviton mode. So then you can ask, okay, so in the literature, there is the result that if you take the dRGT limit, if you do the calculation in dRGT, then the no-ghost condition E2, it should vanish and show a strong coupling problem. So what we do is we take our eigenvalue E2, we apply the UV limit, we apply the dRGT limit, and we find something which is actually non-vanishing. So then you can say, okay, let's do the limits the other way around and see if we still get the same result. So we take the eigenvalue E2, we first apply the dRGT limit, then we apply the UV limit, and we find a vanishing eigenvalue. So you can ask, why is this happening? And so there are two key points here. So the key point is that the order in which we do these limits do not commute. And why this is happening is because once you perform a UV expansion here onto the eigenvalue, we enter a regime of the theory where we can't trust the dRGT limit to be the true dRGT limit. So what we have to do in the rest of the talk, I will be considering both cases in order to not lose any information about the system. So then I'm going to briefly explain a concrete model and give you a clear example that this theory is indeed stable. So as a minimal model, we want to consider what a small departure from dRGT has on the stability of the theory. So what we do is we choose a form for the alpha functions. So we choose alpha 3, alpha 4, which were functions of phi a to be constant. Alpha 0, alpha 1 we choose to be 0, and we choose to expand alpha 2. So 1 plus alpha 2 prime phi a phi, sort of analogous to a Taylor expansion mathematically. And the key point is that alpha 2 prime is much, much less than 1. So the solutions we get should be approximately dRGT. And so with this choice of parameters, the contribution from the cosmological, the effective cosmological constant to the mass term becomes an approximate constant. So you can ask, is this model stable? So what we want to do is you want to impose the following conditions: the positivity of the effective cosmological constant from the Friedmann equation, positivity of the squared tensor and vector mass, and positivity of the vector, scalar, kinetic, and gradient terms. So if we can say all of these are positive, then we have a theory which could be stable, which is stable. So step one, what we want to do is expand all of our quantities around the dRGT value, where subscript 0 represents the value in dRGT, and 1 represents the expansion coming from this alpha 2 prime expansion. Step 2, we want to solve all of our background equations for the dRGT values. Step 3, we have then three free parameters. We have alpha 3, alpha 4, and alpha 2 prime. So what we want to do is identify a parameter space in which we satisfy all three of the stability conditions in terms of alpha 3, alpha 4, and alpha 2 prime. So because of, like I said before, because of the ambiguity about which limit to take first, in this analysis, we consider both cases. So case 1 is when we first do the k goes to infinity or UV limit, and then we take our dRGT limit. And case 2 is when we do dRGT limit, and then we take our sub-horizon or UV limit. So for the vectors, so the action for the vectors looks like this. And so for the vector modes, it's actually so both cases give the same result for the kinetic coefficient and the sound speed. That is to say, if I look at the kinetic coefficient for the vector modes, it's independent. It's not dependent on which case I do first, and the same for the sound speeds. And so we can translate these two conditions into the following relations. So we need gamma naught, which is a function of alpha 3, alpha 4, and alpha 2 prime to be positive, and we need this J1 alpha 2 prime to be positive. So now we look at the scalars. So the action looks similar. However, you'll remember that there was a problem with the scalar eigenvalue. So this is where it is important that we consider both of these cases. And so for case 1 for the kinetic coefficient, we obtain this. And for case 2 for the kinetic coefficient, we obtain this. And the squared sound speed is independent of the order of the limits. So it doesn't matter which of these cases we do first if we want to check the positivity of the squared sound speeds for the scalars. And in fact, the squared sound speed for the scalars is directly proportional to the squared sound speeds of the vector modes. And so from this, you will notice that these actually translate to the same conditions for the vectors. So we'd obtain no new information from the scalars. And these are the two conditions which we have to impose in order. So we impose these two conditions and see it as a region of parameter space in which the theory is stable. So this is the parameter space. All I want you to focus on is the yellow regions. So in the left panel, we have a positive alpha 2 prime, and this is the alpha 3, alpha 4 plane. In the yellow region, the theory is stable. So there are no instabilities, no gradient instabilities, no ghosts. So this is the region in the alpha 3, alpha 4 plane where the theory is stable. On the right-hand side is negative alpha 2 prime in the alpha 3, alpha 4 plane. And the yellow region is unbounded. So So this theory is stable all the way up to essentially infinity in this plane. And the key point from this is that even though the expansions, so the UV limit and dRGT limit, do not commute, the coefficient of the scalar kinetic term in both cases is positive. In the region, the cosmological constant is positive. And so what we have is we have a concrete model of a theory of dark energy in generalized massive gravity, which is stable. And so I will summarize. So like unlike in constant mass dRGT, we have non-vanishing kinetic terms for the vector and scalar gravitons. So this indicates that all 5 graviton polarizations are propagating. And so the strong coupling problem is tamed with respect to dRGT and similar extensions to dRGT, even in the minimal theory. And there is indeed a region of parameter space in which there is an positive effective cosmological constant and no ghost or gradient instabilities. But one of the key points which I want to highlight is that GMG appears to be a stable massive gravity model without introducing any extra degrees of freedom. And this is the advantage that generalized massive gravity has. And so a future work could be checking a working Van mechanism and whether or not this theory, this setup and framework can accommodate a sensible background cosmological evolution. And with that, I will stop. So thank you.
Thank you very much for the very nice talk. Let's thank the speaker.
I'll just want to do that.
Are there any questions? Comments? Yeah, there is one. Another. Sadishi. First.
Okay.
Tashinato.
Hello. Yes, it's me. I'm Giamassimo. So I wanted to ask you, just to be sure I understand. So your theory explicitly breaks Lorentz invariant, right?
No, translation. It's not. It doesn't break Lorentz. So...
It breaks explicitly translation invariance.
Yes. In the Stuckelberg fields. Yeah.
So you can. So this is an explicit breaking. It is not spontaneous that you have some Lagrangian for the Stuckelberg and you have a spontaneous breaking. Here you explicitly break it, right? Just to be sure.
Yeah.
Okay.
Yes. Yeah. So it breaks translation events from this, but it preserves global Lorentz symmetry.
Okay. Okay, thanks.
There is another question from Sahidi.
Thank you very much for the talk. I have a question about the coefficient you are taking. What's the difference of this model with mass varying model? Because I think these coefficients can be absorbed in the mass, and so we can think that the mass is vary with space-time dimensions. But mass varying theory is unstable. How this theory be stable in this way?
So the question is, why is this stable compared to mass varying massive gravity, which is not stable?
Yeah, because I think they are similar.
Yeah, they are similar, indeed. The answer is, to be honest, I'm not sure. But so mass varying massive gravity is so you promote these alphas to a function of some background scalar field. So or not so some scalar field, and so maybe I'm not going to try and pretend I know why that why that happened. But so I think that maybe it's just the setup is different, and this gives you something. So this is promoting. So maybe the answer I can give you is that this is promoting the alphas to something which is already built into the theory, instead of some extra dynamical scalar field which is there. This is the only explanation that I can give you. But I can have a look at the paper and we can talk later and try and work out why, if you want.
Okay, thank you.
Okay. Any other questions? Comments? So if not, let's thank the speaker once again.